to the cloud. Okay, so hello everybody and welcome to the monthly webinar of the new STIG, which is the Infrared Science and Technology Interest Group. My name is Lisa Locke and I will be moderating the webinar today. I'm a microwave engineer at the Jet Propulsion Lab, working on the Deep Space Network, and I'm a member of the STIG Leadership Council. So before I introduce the speaker, I'll provide some instructions on how the webinar will work. I copy and pasted the instructions into the chat. Basically, it just says submit all your questions via the chat, and instead of waiting until the end of the talk, we can actually, put up your questions when you get them, and we'll find an opportune time to bring them out. We'll have a Q&A period at the end. If you have any questions, feedback, or comments for the Leadership Council, you can put them in there too. You can send us an email, report any technical difficulties if you can't hear anything, and I'll watch that and try to fix it. And the webinar will be recorded and available to view later on the webinar webpage, which is noted in the chat. So I'd like to introduce our speaker for today. Dr. Margaret Meixner is currently the director.
I can't hear you now. Is that me?
No, it looks like she faded out.
Okay.
Yep.
Volker, in the interest of time, do you want to carry on with the intro?
Yeah, okay. We welcome Dr. Margaret Meixner, who is currently the director of the SOFIA mission operations. And before she came to SOFIA, she was at the Science Institute, and she worked before on many Spitzer projects. So why don't I pass it on to you, Margaret?
Okay, thank you. Can you all hear me?
I can hear you.
Okay.
They cannot speak.
Okay. Well, hopefully that'll be rectified with questions. Yeah, please do put your questions in the chat. What I'm going to talk to you about today is SOFIA Soaring Forward, and about the exciting current and future science of SOFIA, as well as some of the visions for technology improvements. So the first point I want to make is that SOFIA is the only far infrared observatory for the next decade. And SOFIA will help prepare the astronomical community, both scientifically and technologically, for Astro 2020's ambitious future. So first of all, SOFIA advances the Astro 2020 science by directly addressing one half of the decadal science priorities in all three science themes: cosmic ecosystems, worlds and suns in context, new messengers, and new physics. And the community, can exploit the opportunity SOFIA provides to train the next generation of astronomers and instrument builders who will define, develop, and use the future far infrared space observatories described in Astro 2020. So just going to that point about how much decadal science does SOFIA address. There's a traceability matrix here. This is also posted on our website. And what we've done here is shown the decadal science questions, key measurements that are needed to address them, SOFIA instruments that are required to make these measurements, and then current and planned SOFIA observations. So these, and each of these have a published paper and a program associated with it. Now, this first one, the three themes of the decadal are closely aligned with the three astrophysics science questions. So cosmic ecosystems in the decadal relates to how did we get here, which is an astrophysics division key question. And all questions are from the decadal report. There's a table in there listing these key science questions and priorities. So I'm just going to pick one. Let's just do this first one. How do star-forming structures arise from and interact with the diffuse interstellar medium? And for this, if you want to get that interaction region, the best lines to use are the C2 and the O1 and O1 lines, because those arise in the interaction regions between stars and the molecular clouds from which they're born. Light hydrides are also very useful, particularly in the diffuse interstellar medium. And the spectral resolving power of SOFIA instruments is very high. So you can actually get kinematics of the gas. And then also we can measure far-infrared polarimetry, so we can measure the magnetic fields in the interstellar medium and how they play a role in this interaction. And of course, we can use the GREAT instrument, our heterodyne instruments, which is our moderate resolution, particularly good for nearby galaxies. HAWK Plus is needed for the polarization measurements. And then the terahertz mapper is a potential new instrument that I'll discuss towards the end. All the programs that are here that are in this purple color are legacy programs. So feedback, for example, is one that's measuring these lines at that interface region. Now, cosmic ecosystem, because measurements of the interstellar medium, is an area of strength for SOFIA. We have a number of legacy programs. We have a number of science opportunities for this theme. A second theme, Are We Alone, or Worlds and Suns in Context? Here, this is an area of growth for SOFIA. Again, there are a number of very interesting questions that SOFIA can and has addressed. And if we in this first one, we actually have a legacy program ongoing that's on the moon. So this one is how do habitable environments arise and evolve in the context of their planetary systems? And here the strength that SOFIA has is that we can map a lot of very bright, iconic targets in our own solar system and get detailed measurements that are important context when we observe extrasolar planets. So for example, we can measure water at 99.9% of it. We can measure the oxygen one line, for example, in the Earth's atmosphere, between the mesosphere and thermosphere. Phosphine has been measured or has been observed in Venus. We had a special program last fall on this. The D to H ratio, particularly in comets from the HDO line, is important for understanding the source of water which may have created Earth's oceans. And again, here we have forecast X's in gray, and we have this program about, well, a little less than a year, more than a year ago, we announced this result from SOFIA that we measured water on the sunlit surface of the moon. Now we have a legacy program to map water across the surface of the moon. That's what that program's about. Now, the last topic is one that is very new for a lot of us, but particularly in the far infrared. How does the universe work, or new messengers and new physics? And this point of development that the Decadal points out, transforming our view of the universe by combining new information from light, particles, and gravitational waves. And of course, light is the important component here, what we can do in astrophysics very well. There are mid and far infrared photometric variations, the development of time domain astronomy. And in this wavelength range of the mid to far infrared, the thermal infrared, astronomers just have not had much opportunity to develop even what you can do here. And that's because we've had very limited life missions. The cryogens exhaust out, and then Spitzer, the thermal infrared disappears after 5 years in Spitzer, after 3.5 on Herschel. And of course, the universe is so new, you want to just even map things for the first time. But with SOFIA, people have been using all our instruments, Forecast X's, HAWK Plus, FFLS, GREAT, to look at time variations, particularly for mass accretion events in young stellar objects. That's been the source of a lot of discovery with SOFIA, measuring the brightening, sometimes by a factor of 20. And that is a direct measurement of mass accretion. And of course, there's supernovae. We've been following supernova 1987A in the thermal infrared, finding that the dust is actually not destroyed in the reverse shock. But then also, if a new supernova is to go off nearby, we're going to be wanting to tackle that with SOFIA. All right, now SOFIA science which you've heard comments on, I just want to set the record straight that SOFIA's efficiency and science productivity are on the right trajectory for SOFIA to achieve its full scientific potential. The annual publication rates for SOFIA have doubled over the last 3 years. We're on this uptick. And they're on topics ranging from the Earth. People have used our archive to make measurements of O1 in the Earth's atmosphere to high Z galaxies. I think the record's 3.9. This link that's on this page will bring you to this brochure shown here on the right, SOFIA Science Remarkable Results. A number of these results have come out in the last 2 years. They're very interesting and exciting and offer new windows to understanding our nearby universe. Now, legacy science programs are going to cover some of the science we're doing with SOFIA through the science legacy programs, which now comprise 30% of the SOFIA schedule. We have a pilot phase, which is sort of a 6-month where we give them some data. It's a big commitment on SOFIA's part, so we want to make sure that it's going to work. We have a promotion to full to evaluate that the technique's working, the science is coming out, and they've actually submitted a paper for publication that the team's very dedicated. All the data from legacy programs is public immediately, and we have a number of them. We have annual archival calls. There'll be one later this spring to use and do analysis on these data. And they also deliver higher level data products. So let me just cover the ones that we have. The first one, which tags onto that science I was talking about at the beginning, feedback. The co-PIs are Zandra Thielens and Nicola Schneider. DLR is our partner with SOFIA, and we have a very active German community who work on instrumentation and the science. Now, this feedback legacy program is very relevant to this decadal question of how do star-forming structures arise from and interact with the diffuse interstellar medium. And here they use the heterodyne spectroscopy maps of the C2 158 micron line and the O1 63 micron line in 11 regions. And so they're basically mapping the type of feedback going from simple regions where you have a single star to superstar clusters and actually quantitatively measuring what that feedback is in star forming regions. You know, is it radiation? Is it stellar winds? Is it supernovae? That's what they're addressing. And interestingly, in their analysis of Orion, they find that it's really stellar winds that are the major contributors to feedback. This image you have on the right is showing the famous Eagle Nebula image from the Hubble Space Telescope with those pillars of creation. And then it translates into the great map of the C2 line, where you show the complex kinematics of the interstellar medium that come together to create these beautiful structures. This program is 70% complete. Also with the great instrument, we have HiGal, which is characterizing the galactic interstellar medium with observations of hydrides with the great instrument. This is led by Dave Neufeld. It's 42% complete. And what they're doing is using absorption line spectroscopy to a number of sources of multiple hydride molecules. This is showing SH. And the key thing about hydride molecules like SH or CH or OH, a lot of their ground state rotational transitions are infrared. So the only way to make these fundamental measurements is with SOFIA or in the far infrared. They use these to constrain astrochemical models of the turbulent interstellar medium. So these are very key, important observations, and they address 3 decadal science questions. How do gas, metals, and dust flow into and throughout the galaxies? What regulates the structure and motions of molecular clouds? And how does gas flow from parsec scales down to protostars and their disks? And their magnetic fields. This is an area that SOFIA is really revolutionizing our understanding of star and galaxy evolution. GalMag is a legacy program led by Enrique Lopez Rodriguez. He's mapping the magnetic fields of galaxies with the Hawk Plus camera. And below you can see the diversity of magnetic field structures that they're unveiling. You have M82 on the left, which is a starburst galaxy with this immense galactic wind. And they find that the magnetic field is threading and supporting this gas outflow. You have the merging galaxy of Centaurus A at the center here. And here you can see the magnetic field confined to the disk, the dusty disk here. But not only is it confined there, but the structure is very erratic on the fine scales. And this is due to the amplification, due to the turbulence in this merged galaxy. And they suggest that mergers may be important for amplifying in magnetic fields throughout the history of galaxy evolution. And on the right is the classical star-forming galaxy, the Whirlpool galaxy M51 with its interacting neighbor. And you can see that the spiral structure is imprinted. The magnetic field has that imprinted, but again, on the smaller scale, you can see the turbulence, probably due to stellar feedback, is amplifying those structures. And again, this legacy program addresses these two decadal questions. How do gas, metals, and dust flow into and out of galaxies? How do star-forming structures arise from and interact with the diffuse interstellar medium? And we're looking closer to home with magnetic fields. We have actually two programs, one field maps, which is filaments extremely long and dark, and it's a magnetic polarization survey. It's led by Ian Stevens. It's 51% complete, and this is one of the very dense and dark clouds that they're measuring the magnetic field strengths for. And this is important for understanding what regulates the structure and motions of molecular clouds. The turbulence, is it magnetic fields? What are their respective roles? And SOFIA is providing the first detailed measurements for a number of objects, so you can actually quantify and gather statistics. And then it also investigates how gas is flowing down to protostars and their disks. What is the role of magnetic fields in the star formation and planet formation of these systems? And then on a nearby target list, Thushara Pillai is doing a study of interstellar magnetic polarization, a legacy of filaments, or SIMPLIFY. Her pilot's been completed. This is basically doing magnetic field measurements in nearby filaments, the classical nearby things like Serpens or Taurus. This is a follow-on to her amazing paper in Nature Astronomy, where they map the magnetic field structure down to the collapse of the star and really quantify the importance of magnetic fields and how it controls the flow of gas. But in the end, when the density really gets really high, they align with the filament and allow the gas to flow into forming this cluster. That was a really interesting breakthrough paper. And again, she's looking for that again and to get statistics on a variety of nearby sources. There's one that is up and coming, LMC Plus. This is a survey of the C2 line in the Large Magellanic Cloud, led by Sue Madden. The pilot's coming. We're going to Chile in March to map this. This is done with FIFI-LS. They're mapping the C2 158 micron line in the South Molecular Ridge. And so this is an image I really like, with Herschel and Spitzer together in the Large Magellanic Cloud showing the South Molecular Ridge. And they're also getting the 0388 micron line. And this complements ALMA data in two ways. One is there's a map of this region, but also the analysis of C2 and O1 in this nearby lower metallicity, lower than the sun analog. You can actually calibrate and understand where the C2 arises from, what the O3 actually means, because these measurements are made in high Z galaxies with ALMA, and we're able to kind of interpret the microastrophysics of what's happening with these lines by looking in the Magellanic Cloud. This again addresses three questions. We've talked about star-forming structures, their interactions, the metal flow, but this one here, how do the histories of galaxies and their dark matter halos shape their observable properties? Again, this needs nearby universe calibration as well as high redshift measurements. This is our completed legacy program. This one was done by Matt Hankins. I'm gonna correct this and send you the slide deck, but this is led by Matt Hankins, and they mapped with SOFIA this galactic center region, which has a lot of extreme star formation. It's our first legacy program that we completed. With SOFIA, we looked at with forecasts at 25 and 37 microns, and that nicely fills in the maps that have been made with Herschel, as well as with Spitzer. Now, a new program that we have a pilot phase for, Galactic Center Magnetic Fields, led by Save Schus, complements this forecast legacy program. Again, it's looking at the galactic center. It's an area of which we have a lot of data that we've been collecting with SOFIA. It's to map the magnetic fields in the central 200 parsecs of the Milky Way with the HAWK Plus instrument. And so here we have down below in blue that shows the outline of regions covered by forecast. And here we have examples of predicted magnetic field strengths. The measurements of the magnetic fields in the thermal infrared where the stars are forming is really a much needed piece to understand the star formation going on here. What is regulating the formation of massive stars in this region. These magnetic field measurements will be key to understanding the role of the magnetic field, which we think will be important based on our other measurements that have been made with HAWK Plus. Also, samples of near the galactic center. We know we have a supermassive black hole there. We can measure the magnetic fields around that, and we can understand a bit more about how what seeds and supermassive black holes and how do they grow? What's the role of magnetic fields with that? Last but not least, lunar, this water on the moon legacy program. It's only 4% complete. It was just promoted to full legacy a few weeks ago. It uses the forecast GRISM mode. And it is a follow-up to the first direct detection of molecular water on the sunlit surface of study. And it's to study the distribution of water across the lunar surface and also the time variation due to lunar cycle. And again, this is important to understanding how do habitable environments rise. We all think that water is a key to life, and the presence of water, how it's distributed and how it's retained is important. All right, so we have a lot of exciting science coming out, and that's just a highlight from legacy programs. There's, of course, a lot of very interesting geo programs as well that are coming out with fascinating results. Let's talk just a little bit about SOFIA in the context of other observatories. So this diagram shows how light comes to the ground when it gets all the way to the ground, like it does in the optical and the radio. You can see that we can have ground-based observatories. But when you get to the high energies over here, or when you get to these mid-infrared wavelengths, it gets a lot harder. You have to get high up to get above the water vapor. And of course, if you're in space, you're golden, right? And then this far infrared wavelength range is the key wavelength range that's blocked from the ground. And this is where SOFIA comes in. So that's the height at which SOFIA comes. It tries to get above, like I said, 99.9% of the water. So you're just at the right height to get and have access to this wavelength range. So that's the key importance of SOFIA and what it can offer observationally. Just a little bit to remind you what SOFIA is. It's a 2.7 meter telescope. It has an effective area of 2.5 meters because we have nutating secondaries. It's reflective for wavelengths from visible to the submillimeter. It's very nimble. It's excellent for mapping. So things that people have done before with Herschel or Spitzer, we can map, particularly with Herschel, we can map large spectral areas. It has a chopping secondary, an optical guide camera, and it is a warm telescope. So that produces a very high background. So it's very different in what it will achieve than, for example, a future far infrared probe. It's very complementary to what people are discussing future missions. We have 5 science instruments and also this focal plane imager, which has been used for occultation experiments. This is forecast with both has an imaging, but also GRISM spectroscopy mode. There's the high resolution in the mid-infrared with XEs, very high spectral resolution, 4.5 to 28.3. There's HAWK Plus, which is, I've talked about a lot about the polarization, but it is also, you can get photometric measurements within the 50 to 240 micron range. There's FIFI-LS, which is the far infrared field imaging line spectrometer. It's great for nearby galaxy work, 51 to 203 microns and 600 to 2000 spectral resolving power. And then there's GREAT, which is the German receiver for astronomy at terahertz frequency, going from 63 to 612 microns, and of course, ALMA-like spectral resolution. This shows how SOFIA instruments are complementary to its contemporaries. James Webb, which is fabulous, how well it's working, and ALMA, which of course has been working for quite a number of years. So this is spectral resolving power. And one of the strengths of SOFIA is we have very high spectral resolving power instruments. So James Webb's here in the dark gray, and you can see we of course have imaging with forecast and HAWK Plus, but with GRISMs with forecast, and then particularly XEs, we have higher spectral resolving power that can complement and investigate different things, supporting things for what we can do with James Webb. Of course, we are the only instrument in the far infrared now. That's where we see great FIFI-LS and HAWK Plus. And then we have ALMA here, which of course will be constrained by whatever the water vapor cloud above it. And there is a lot of water vapor lines here. So GREAT has access to a number of lines that we can't get with ALMA. This shows you the complementary nature and continuum sensitivity. So we have forecast and JVST, which have similar wavelength range, but they look at different objects. So forecast looks at really bright objects. Things that would saturate. So this faded gray region here is what is JVST unsaturated. And of course, it gets incredibly sensitive. I mean, that is the strength of James Webb, to look at faint, particularly distant things. And we can look at bright, iconic objects and calibrate them really well. And then of course, HAWK Plus is the only bolometer we have, and it has a polarimeter. Spectral line sensitivity, also there is this complementary nature. Here's JVST unsaturated, and here's where XEs is, and they complement each other against the types of objects that they can look at. And then here, again, the only game in town in the far infrared is SOFIA. We have the GREAT instrument with these different line sensitivities, FIFI-LS. And as I'll discuss in our instrument roadmap, there's a potential to have things like a terahertz mapper or direct detection spectrometer. Now, I'd like to say when looking at SOFIA and James Webb that basically SOFIA and James Webb together can cover the universe. We have a little just comparison. They're really just talking points at the moment. We're working on more of a scientific guidance with plots, but this just is talking about some of the talking points about SOFIA and James Webb and how they work together. So again, SOFIA is the only far infrared observatory, whereas James Webb is the largest space observatory in history, working at the near and mid-infrared wavelengths. SOFIA has this ability to fix, update, and replace with new instruments to meet new science demands, so it can evolve on a fairly quick timescale. And James Webb is a robust design, as I'm completely marveling at the unfolding of James Webb and all the success it's having. It has a 10-year goal. It's not serviceable with new instruments, but it's going to last and provide lots of wonderful data for us. SOFIA can probe bright, iconic objects that are too bright for James Webb. For example, the moon, which James Webb can't even point at. We can provide information on. But of course, James Webb is going to look at distant universe objects, faint nearby objects that are just out of the range of SOFIA. SOFIA can do detailed observations, particularly with the high spectral resolution of nearby universe that can calibrate the more distant objects observed by James Webb. And JWST offers detailed observations in near and mid-infrared that complement what SOFIA finds in the far infrared. Now, we have lots of science opportunities with SOFIA. We just had our cycle 10 call. I hope you all submitted your proposals last week. I look forward to reading them. The deadline was January 28th. We will have future calls, but the observing time, I want to point out, is increasing with SOFIA. The project's figured out the best way to retool to get the most observing time safely. Safety is important to them. We have 50% more time available in cycle 10 than we did in cycle 6. And not only that, but we have 2 times more observing opportunities in the Southern Hemisphere. So we have 3 Southern deployments in cycle 10, and we will be cycling the instruments through. So each of the instruments will have access to Southern Hemisphere targets. So for the GEO programs, we offered 550 hours in the GEO programs, and legacy programs 200 hours. We have a minimum grant size of $75,000 for observing programs because we want to ensure that you are fully supported to get your papers and your data analyzed and your papers published. We do have a new multi-cycle time domain category. Again, this is an opportunity for the community to develop the field of mid and far infrared time domain astronomy. We had a local supernova science team. We were recruiting members to define what that program might look like. Should we get another 87A opportunity? And SOFIA offers joint observing programs with the Green Bank Telescope and the Infrared Telescope facility. And we have a category for SOFIA programs with JWST Synergy. I encourage you to join the SOFIA community. Our SOFIA user community of investigators and authors is 2,138 strong and growing. We grew 12% last year. And our virtual science workshops and other community engagement activities have increased on our wider SOFIA community size by an additional 30% of new to SOFIA astronomers. To learn more about SOFIA opportunities, I encourage you to visit our website. And now I want to get a little bit more onto talking about future of SOFIA, the context on how we can value the SOFIA opportunity. So first of all, SOFIA is an important suborbital mission. And suborbitals like SOFIA are essential to further science and technology to be used in future space missions. The balloon program, which is another substantial suborbital portfolio, focuses on PI-driven far infrared observations. Far infrared technology developed in balloon platforms can be applied in a more capable instrument on SOFIA, which has larger aperture, power, mass, and volume envelopes. SOFIA offers the only reliable, repeatable suborbital platform. And the astronomy communities, your proposals are what direct SOFIA's observational program. Instruments can be upgraded or replaced with new ones. I view it as a stepping stone between the blue balloon program and what could happen with in space. So for example, on the Origins Space Telescope study, we utilized the HAWK Plus instrument as a base design for what we might put in the FIP, the far infrared imaging polarimeter that we had in the concept design for Origins. And then most importantly is that SOFIA can support a diverse science opportunity for the astronomical community. Now, SOFIA has been operating during the COVID pandemic. It's a human crewed mission. And if you are a PI of a SOFIA proposal, you can have the opportunity to fly with us. We have been, safety of course is the #1 priority in any SOFIA flight. And they've been flying safely during COVID. On the right is a picture taken during the observations of Venus. And you can see everybody is masked. People remain socially distant. They use a combination of surgical, N95s, and face shields, and of course testing. They did, it's a very heroic and dedicated team. It's been one of the pleasures being director of SOFIA, is meeting this team that is just awesome. They have been doing flights from Palmdale. They did a deployment in Cologne, Germany, and a year ago. They did a deployment in French Polynesia over the summer, and they're about to go on deployment to Chile in March. And one of the other fun things to do is to follow SOFIA as it flies. So SOFIA typically flies 4 times a week, Monday through Thursday. And you can follow SOFIA on flight trackers. And my favorite is FlightAware, where the link's there, and you just type in NASA 747, and you can actually see it as it goes through its flight path. Just jumping ahead and thinking more about this opportunity that SOFIA has in the development of instruments and also the furthering of science. We developed a year ago a SOFIA instrument roadmap, and this is a science-driven exercise where we ask the community what are the most important science questions that you can address in these wavelength range. We compile those cases, and we assess what would be the most important type of instrument to focus on. And that's what this roadmap encapsulates. And there's a link at the bottom that you can click on to see the full report. But I just want to touch on some of the highlights. So first of all, SOFIA can actually increase its capability by up to a factor of 10 in better sensitivity or mapping speed with a new instrument. So we have 3 steps. Let me just point out here these 3 steps here. There's an instrument upgrade, a new instrument, and a new instrument. And you can see the timelines here are to have cadences of a few years in between these drops. The first one, which I'll talk about first, is an upgrade to the Hawk Plus instrument. That's expected in 2024. And you can see we have various other missions that we can help respond to with these improvements. And then there's this future potential far infrared probe, which I hope you'll get to hear about in a different webinar. So step 1, replace the Hawk Plus detectors to increase the mapping speed for magnetic fields by up to a factor of 4. And this is because Hawk Plus has been revolutionary in trying to, in elucidating what types of effects magnetic fields have on star formation, galaxy evolution, and black hole accretion. And it's in what we call a formulation phase, which have funded both Goddard Space Flight Center to investigate replacement with TES bolometers, and NIST to investigate the use of MKIDs for detector replacement. And the formulation phase is basically to do a study of what would it take, what would the result be, what would the cost and schedule be. And that's going to be evaluated late spring and summer before proceeding. So we're looking forward to that. And step 2, there's a lot of science you can do at this wavelength range, and there are 2 competing and completely different science-driven instrument concepts. So concept 1 is to build and implement a direct detection spectrometer. It's 30 to 120 microns, high enough spectral resolution that you can get some kinematics around protoplanetary disks. And one of the science drivers was measuring the mass of protoplanetary disks using the HD line as a proxy for molecular hydrogen. And this is because it's been found through a number of observations that the CO is probably condensed onto grain, so it's not as good as a tracer as HD. The key driver here technologically is detector sensitivity, and of course you need an array too. So we need more sensitive but bigger arrays as well. And we need improvements by a factor of 10 to hit the science goal, and investigations of TES, transition edge sensor detectors, and kinetic inductance detectors were both possible avenues. And the second concept is to build upon the success of GREAT, and that is shown here, maybe most pictorially on the left. This is the Horsehead Nebula in the optical, What we have now in terms of a footprint from GREAT, the upgrade instrument, is these big hexagons. And the idea is to fill the focal plane with a number, sort of 100 pixels, to get a bigger map and to be able to map much quicker by a factor of 13 than what the GREAT instrument is. So that means you could almost be able to do snapshot surveys of some of these regions that feedback has been doing. Utilizes the whole focal plane, and it's complementary to these balloon surveys that will be coming online, like GUSTA, where they do lower angular resolution mapping of large areas, that you can get more detailed studies with something like this. Now, touching on to the decadal survey, which I know you've all heard about in the context, and just the decadal context for SOFIA. So sitting for where I am, to me, the current and future science for SOFIA is very exciting and it's very compelling. And over the past 2 years, SOFIA's experienced a tremendous scientific growth. SOFIA has addressed and implemented all of the flagship mission review recommendations that has caused this improvement, I think, in its productivity. Now, the ASTRA 2020 comments are based on information sort of pre-March 2020, and they missed this growth of SOFIA. It's been put in a static box. So I think that's just a factual point. A later committee reviewed what we were doing and how we were pivoting, and this is the NASA Astrophysics Advisory Committee, and they applauded the recent efforts to improve the scientific productivity of SOFIA in their letter in their March 2021 meeting. The decadal acknowledges the importance of the senior review process, and SOFIA has a polished proposal for senior review that represents a very strong case for continuation. Now, we recently learned about 2 weeks ago that NASA headquarters has decided to remove SOFIA from the senior review effective January 14, because they decided to take the decadal report input to their review process. Now, the decadal is a wonderful process. It has a lot of fabulous things in there, but it's very high level. It's a very different type of review and analysis than the senior review, which is more in depth, more current, and more thorough, just by the nature of the constructs of the review. So I want to also address some of the comparison sets that people have been making, for example, in the ASTRA 2020 decadal, and provide maybe a more proper context to how to interpret and value SOFIA. So SOFIA versus space mission, I've been mentioning it's a suborbital mission. And along those lines, the timeline for SOFIA's success is quite different from that of your typical space-based mission, where space-based missions have high launch costs, expendable cryogen supplies. Operations are relatively inexpensive. That is, you build it up, you launch it. We hope everything works. And then you're in operations, and it's robotic at that point. It's collecting things 24/7. SOFIA, on the other hand, had zero launch costs, has replaceable cryogens, but operations include spacecraft, maintenance, fuel, and crew. It's a human crewed mission, and this provides an excellent also training opportunity for the astronomy community and instrument builders, because you actually get to touch things and understand how they work in a very deep manner. Now, as an airborne rather than space-based observatory, SOFIA also has less time per sky because we have people involved. Now, these factors were built into the SOFIA design model from the beginning. It included a slow ramp up towards scientific success, which was compensated for by long mission lifetime, made possible by replaceable cryogens. I mean, when we had Spitzer and Herschel, they had consumables, and the thermal infrared was gone after a few years. Whereas SOFIA, we can do this for 20 years. And so judging SOFIA by space-based mission model sets inappropriate expectations for its science productivity. And similarly, if space missions were judged by the airborne model, they would never get off the ground because you would never be able to finish building it. So let's go back to publications and where SOFIA is. So this is data. In the dark is where we are scientifically in terms of science. And these are the science publications. We have some that are based on observations. We have a growing wedge based on archival. And if you look at it from where I stand, SOFIA is currently at an inflection point of its growth in science publications, similar to Gradient, where you have in early years for space mission, there's an uptick. But the ramp is going to be slower for the reasons I mentioned. Where are we now? Total publications now, we have 281 publications. We predict, and the rate has doubled. The annual rate of publication has doubled since 2019. I mean, 3-year time span, we've doubled the annual rate. If you go 3 more years out, we expect to double it again. And so it's on this uptick, on this inflection point. And at some point, you know, we'll hit a more steady cadence where the increase is going to rise mainly from archive, which is true of very mature missions like Hubble. Now, technical publications, we have 81 of them. So they're almost at the moment a third of the science publication. And that really demonstrates some of the value of SOFIA to the astronomy community in far infrared technology and instrument development. We really help advance and explore that. So including technical papers, SOFIA actually has a total of 362 papers. And this is in line with expectations of the airborne model. Now, our conservative projections indicate that SOFIA is going to reach over 100 publications per year by 2024. And this was actually the goal set by the flagship mission review. It says, you know, you need to be up here on an annual basis, and we will be there in 2024. We have identified and incorporated the flagship mission review recommendations, and this is what's going to get us there. But it takes a couple of years. Because it takes you all a couple of years to write a paper once we give you the data. So we expect these increases in publication are a result of SOFIA's intentional programmatic changes, increasing flights, increasing investment in archival research, and innovation we've done in the science operations. Citations and H-index, so SOFIA's impact is also growing. Everything up to this grade area is data. And what we have here on the lower level, like what are our projections for impact, are basically based on a fit to all the data. So it's super conservative. The upper line is basically over the last 2 years, we've of course been having an uptick. And this is an extrapolation based on that uptick. We expect to be somewhere in the shaded area. But again, this is just to point out that SOFIA is actually on an uptick of producing the science for the community. Now going back to, again, what should you compare SOFIA to? Like what should the expectation be? Comparing it with other space missions. So SOFIA's science publications, 281, are significantly higher than the science return from far infrared balloon missions, which are 8 now. This doesn't mean that SOFIA is better than balloons. They just have a different purpose. Balloon missions are phenomenal at trying out new technology, testing new things that can be then implemented and built upon in more ambitious things like a SOFIA instrument or a space mission. Now, SOFIA has been compared to Hubble, which is a mature, about 30 years, robotic mission with a substantial archive. You know, a better comparison really is with Herschel, which is a recent far infrared mission that's provided over 22,000 observing hours, produced 900 publication. And SOFIA has observed for about 4,000 hours, and it's produced 281 science publications. And so SOFIA has already passed Herschel in paper writing efficiency, but not total papers. But over its operational lifetime, SOFIA will produce a similar number of observing hours and publications as Herschel. I want to point out something that the STIG has done. They have a forum, they published people who had endorsed this letter of support for SOFIA. And if you're so inclined, we can still collect names for that. I'm going to stop there, and hopefully we can have a discussion and questions.
Okay, thank you very much, Margaret. That was great. Let's see. So there's no questions in the chat. So if you're interested, oh, there's some hands. Okay. Kathleen, I saw your hand first. Just feel free
yes.
to unmute yourself.
I've lost my question, so if you could come back to me, sorry.
Okay, no problem. Anyone else? All the hands went away.
Oh, okay.
Okay, so if you have a question, just unmute yourself, and let's do it that way.
Yeah, I found my question. I was wondering if Margaret, if you could put the website link to where the JWST, SOFIA, and particularly the Astro 2020 comparison, the charts that map from SOFIA's capabilities to the various points in Astro 2020.
Okay. I don't know. Okay, well, I did put the link here for the James Webb comparison, but that's not what you're asking.
Yeah, I got the James Webb, but I thought you had one for the Astro 2020, those comparison charts.
Oh, I should.
Yes, the
but I don't have
traceability
it
matrix.
Here. Okay. You know what? Let me. I will provide this slide deck. I can maybe put it in the chat. Maybe that's what I should do here. Yes, that
Great,
is.
thank you.
Yes.
This is Mike Warner. Can I make a comment, Lisa?
Yes,
Can you hear me?
yes, you can. Go ahead.
Yeah.
Yes.
Margaret, it's an extremely compelling story that you put together very, very well about comparing space and airborne missions, because in space, of course, you get wavelengths you don't get, and background conditions you don't get from the aircraft altitude. My question is, can you say a little bit more about the joint programs you have with the IRTF and I think the GBT, and whether you see that kind of joint program as a growth area for SOFIA going forward? Very, very, very good story you've told us about.
Okay, first of all, just to get back to Kathleen's point, I just put in the chat window the website for the SOFIA science traceability matrix that shows how we map on basically to half of the decadal priorities. Yeah, and as you all know, they said we had 3 questions. We actually covered 15 of them. And, maybe in hindsight, SOFIA should put in more white papers, but because we cover such a broad range of capability, we actually address quite a lot. Mike, going back to your point about a joint program. So we have the IRTF joint program is new with cycle 10. We, of course, historically have had people who've used IRTF and particularly TEXES and EXES, but we'll find out how many are multi-observatory. For GPT, we have, I think it's 3 programs that are joint with GPT using SOFIA data and GPT data, and most of it's come in that direction, that we had people who applied for SOFIA and wanted GPT time. And so we have 3 of those programs. In this, for James Webb now, we actually did a little archival work, and there's 28 proposals we have in SOFIA that are sort of scheduled programs that mention JWST. There are 4 that sort of highlighted that, hey, we have JWST time, ERS or GTO time. But there are 28 who talk about the synergy. And of course, we had enticement for people to apply for SOFIA time that was synergistic with their cycle 1 programs. Again, we're still sorting through all those number of proposals, but I'm hoping that but I was encouraged to see there are like 28. We'll be investigating at least science synergies, and if not we'll discuss the viability of having joint calls, but certainly the science synergies are there. Did that
Thank you very
address
much.
your question? Sure.
Okay, and Luigi, you had a question?
Yes, just a couple of comments. The first one, I'm pretty amazed by the fact that the cattle survey has a big contradiction. They say that infrared, in particular far infrared, is the way to go. Also, after the cancellation of SPICA, the Americans are going to cover that area. And at the same time, they say very bad words about SOFIA, which is the only far infrared observatory which is running now. The second point is after almost 10 years of last operation of Herschel, of course, SOFIA is going to interest people more and more because we have experience with Herschel data, the importance of far infrared data, in particular spectroscopy, but not only spectroscopy, imaging and polarimetry, of course. And so the growing interest on SOFIA is also because it's 10 years that we do not have any other opportunity. Okay.
Yes, thank you. Thank you for those comments. I couldn't have said it better, that we need SOFIA to be around to, I mean, that's like 2 PhD cycles, and people have new ideas. Herschel couldn't look at everything. And SOFIA has a lot, I mean, the great instrument has comparable or better sensitivity than Herschel Hi-Fi, for example, because it can improve its instrument capability. It has that, that ability. And I look forward to this sort of being, again, a springboard. It would be complementary. It doesn't replace a far infrared probe. We absolutely need a far infrared probe because, again, the temperature of the SOFIA telescope, room temperature. So you have this huge background, and you will only get rid of that when you go to space. And a far infrared probe will be looking at completely different types of objects that will allow to explore much deeper. I mean, you know, from your work on SPICA, you can go very faint and far, which isn't what SOFIA is going to do. And at some level, you kind of need both. You need to be able to look at bright nearby things, which is what SOFIA will offer, and you need to look at fainter, more distant things. And I think they're very complementary to each other.
Okay, we're just about at the end of our webinar. So thank you for joining us for another webinar, and join us for future ones on the first Tuesday of every month at the same time. If you're interested in speaking at a future webinar, or you'd like to nominate someone as a speaker, please contact anyone on the Leadership Council with your question. So, there was one more question. Oh,
Sure.
Thomas.
I could be here.
Thomas Nicola.
Yep. Well, it was actually an applause, but I also actually do have a question. So, how do I interpret that the detailed review basically blasted SOFIA, but then the advisory committee is recommending SOFIA? How should I interpret this? Is it now sort of time to rejoice and say hooray, or it's we have a very bright future, or what is the?
Yeah, let me, if I could just go back to this plot on publications, just for a moment. So the decadal had out-of-date information, which I suppose would have been adequate if SOFIA were static, right? So it's taking data from like this point here. And if you just move that across, it doesn't look very impressive. But the thing is, we're on this growth curve. And I think and literally these very high profile results on Serpens, on the moon, on these other things came out after the decadal stopped collecting information. So it's one of these things where we're dynamically changing, greatly improving the science predicted, which is important. It's what they measure. It's important. So I think, I'd like to think that that the decadal survey would have wanted us in senior review, so you could get a more thorough investigation. Has SOFIA addressed the flagship mission review comments? I mean, that's important. Is it paying attention to its community? And the truth is it has, but it's really transformed and it's a credit to this team. This team is really phenomenal that it was able to pivot so quickly and change how it was doing things to improve the science productivity. And so that's how I, the decadal was, if you will, here, and then, the APAC had all this high impact science that had come out. And so they can see that SOFIA is changing and improving. So I think, if you do data points, and we had viewed senior review as being another point up the curve to show the high science productivity. So I think it's in part because maybe people did not expect SOFIA to be able to change so quickly.
So do you think that given, even so that it has been removed from the review for this year, that the advisory committee, given that they actually gave the thumbs up, it will be put back, or there will be some review and then there will be a bright future?
I don't run the review process. We do think it's important to get this information out, so stay tuned. We, of course, would love to be back in senior review, just so we have that the clear case to get community review. But stay tuned. I will keep you all posted, and I don't know, maybe I will try to come back to the IR STIG just to give an announcement as where we are in a month. Actually, in a month from now, we are in our conference at Lake Arrowhead. We have a and I should have put a slide. I will add a slide, Lisa, to this. But we have the deadline for abstracts and registration are February 14th, and the conference is February 28th. It is in person, but we have high level of security against COVID. We're very practiced in this with flying in it. We'll certainly provide that community with an update, but I could provide you all with an update for where we are. But certainly as director, I think this mission is very important to fight for. And then that is what I'm doing.
That would be great, Margaret. I'll say, I don't want to push you beyond the 11 o'clock or the hour.
If there are questions, though, I'm happy to address them.
Okay. All right. Yeah, we have a question from Jens.
Thanks, Margaret. That was a really interesting talk. Can you explain a bit more how you produce this particular curve, this particular figure?
How I can use it as an argument?
How you produce it.
Oh, great. Well, everything in dark colors are facts. I mean, that's from, we comb the ADS website to see what, and we have criteria for what's a SOFIA paper. It has to be using SOFIA, data or modeling of SOFIA data. And then the predictions are based on flight hours. So we've been increasing our flight hours. And so that's fundamentally why it's going up. It increases not only just the observational papers, but it also increases the archival size. And it is a conservative curve because it's based on things that we can quantify, like the number of hours, the size of the archive, improvements we're trying to make, and innovation to scheduling using water vapor information. The schedulers are like magicians in terms of how they get things scheduled, and they're adding improvements to that. It's conservative, I say, because we also have community engagement programs. So, for example, tomorrow through Friday, we are having a SOFIA school. I think there's over 260 registrants. It's virtual and free. I hope that your postdocs or students are attending. I think it'll be very valuable to everyone. And it's not only what SOFIA can do, but what types of analysis can you do with the data? This is not things that people teach in undergraduate classes. And so we're trying to provide training opportunities so a wider range of community members can take advantage of SOFIA. So anyway, going back to this, we don't know how to quantify the effects of better science outreach programs. That's not included in these curves. It's basically using past performance, how SOFIA has done, and just the increase in hours.
Yeah, thanks so much.
Sure.
Okay, well, thank you all for attending, and thank you very much, Margaret, for this great presentation.
Sure.
And we'll see you guys next month.
Right, and I'll, I guess, email you all a link to get the presentation, so you have a more complete one. Okay, great. Thank you.
Thank you, everyone.